Hello there, this is Alana Tuckey, and I'm going to be helping you here with section 12.1, number 27 from the study plan. Okay, so let me grab an example that's similar to this. Oops, I think I did the help me solve this, my fault. View an example. There we go. Okay, so we have, according to a census company, 8.1% of all babies are born are of low birth weight. An obstetrician wanted to know whether the mothers between the ages of 35 and 39 years give birth to a higher percentage of low birth weight babies. She randomly selected 350 births for which the mother was 35 to 39 years old and found 30 low birth weight babies. Complete parts A through C below. Okay, so if the proportion of low birth weight babies for mothers in this age group is 0.081, compute the expected number of low birth weights to 35 to 39-year-old mothers. All right, so you're looking at 350 births. So what you want to do is you want to take 350 and you want to multiply it by your P. So that's your N, and you want to multiply it by P, which is 0.081. Enter. Which gives you 28.35. So that'll be the low birth weight babies. And then you have the non-low birth weight babies, which would be, well, 350 minus that, right? Or if you like, 350 times 0.919, the complement. So if 8.1% of them are low birth weight, then 91.9% of them are not. Notice these two numbers add up to 350. So you could also have found this by taking 350 and taking away 28.35. That would also work. Okay? All right, so there's your expected values. Your observed values are, oops, she randomly selects 350 and she observed 30 low birth weight babies. So I put that into StatCrunch here. So I had the observed was 30 low birth weights and then 320 non-low birth weights. And then we expected 28.35 and 321.65. All right, so now let's see what else do they want. So we figured out the expected values. Oops, see 28.35 right there, 321.65 just like we came up with. And then, the observed values, we already did that. That's 30 and then 320 because that would make 350. And then they want us to test the claim, right? So answer the obstetrician's claim using the chi-square goodness of fit test and state the null and alternative hypothesis. So the null hypothesis would be, right, that the proportion of low birth weight babies is what they said, 8.1%. And the alternative to that, this person is arguing a higher percentage, so that's a greater than. Okay, so let me go grab StatCrunch. Pretty simple and straightforward. So I go stat, goodness of fit. It's a chi-square test. Observed is in the observed, expected is in the expected. Compute. And there you go, 0.746 or 747. So let's see if that matches what they did. Yep, see right there, 0.746 right there. Close enough. All right, so there's the p-value. But if you'll notice, your null hypothesis is extremely simplistic, right? So you're not rejecting the null, blah, blah, blah. But then did you see here how your null was only, the proportion is equal to, there it is, proportion is equal to 0.081 or proportion is greater than 0.081. So very, very small. So that's basically the same hypotheses that you were testing back in chapter 10. That's really a 10-2 question. And so they're saying, okay, well, instead of doing it with the chi-square test, why don't you do it with the same basic thing you learned back in chapter 10, which is that if n times p times 1 minus p is greater than 10, then you can use the proportion test with a normal curve. So let me go grab that. So instead of doing this chi-square test business, what if we do stat proportion, one sample with summary, and we say we had 30 low birth weight babies. We had 350. Or was it 300? I think it was 350. Let me double check. Oops. Because this is such a basic proportion problem. It's basically a chapter 10 proportion problem. Where do they have it? Oh, right up there, 350. Okay, so let me go grab StatCrunch. There's 350, and I'm testing 0.081. That was my null hypothesis. My alternative was a greater than symbol because they said the words greater than. She thinks it has a higher percentage right there. Higher percentage, that's greater than. All right, and then I'll go to compute. And there's my p-value. Now there's two different tests. It's the same kind of hypotheses, right? But the top one is running off of the normal curve, right? You're assuming you have the normal curve. That's where a z statistic comes into play, because that's the normal curve statistic. And then your p-value is only 0.3732 because you're running the test as if the data were normal. So you're saying my sample size was large enough that n times p times 1 minus p would actually work out. Remember, that's the quality that would make it large, or if it's larger than 10, then it would make it basically a normal distribution. The other test that you're running is not assuming a normal distribution. Well, it is, but it's a different kind of test. It's running it as a chi-square test rather than as running it as a normal test. So in that case, your p-value is 0.7465. So the same data, but you can run two different tests from it. You can only run the top one if it's this very, very simple chi-square that has two values. So if you're doing a chi-square goodness of fit test that has two values like this, then you can actually run it as a normal test like this. Of course, as long as n times p times 1 minus p is greater than 10, which it was in this case. All right, so that's that. We've run the tests, both of them, and that would give you p-value 0.373. Now, if you're on a calculator, to run the chi-square test, you'd have to edit, clear, over here, clear. And again, only TID4s can do this. So you do 30 for this, and this is 350, take away 30. That's 320. And then over here, we had 0.081 times 350. And then this is 0.919 times 350. And there you go. And then you run, and let me double check that real quick before I do it. Yep, 321.65, that was correct. All right, then you say stat tests. And since it's so close to the bottom, it's easier to go up with the up arrow and kind of work your way up to letter D. And then L1 and L2 is where everything is. Your degrees of freedom this time is your number of categories, take away 1, so it's only 1. So you only have 2 categories. Those are the times that you often can use a proportion test instead. So the goodness of fit test, there's the p-value, 0.7465. And if you have a degrees of freedom of 1, you can actually use your one prop z-test instead. But only if n times p times 1 minus p is greater than 1. Or greater than 10, excuse me, greater than 10. So 0.081, you had 30, 350. You want a greater than, so use your arrow keys over here and press enter to get the greater than highlighted. And go down to calculate. And there's the p-value, 0.373. So you're running 2 tests off the same data. One is a chi-square test and one is a p test from chapter 10. So one uses the chi-square distribution and one uses the standard normal distribution. All right, I hope that helps. See you later.